Okay, so this video will be talking about homework 3 of module 5 chemistry on calculating equilibrium constants. Okay, right. So multiple choice. First question: what information can the equilibrium constant KEQ of a reversible reaction provide? Yeah, it can provide your position of equilibrium given a certain temperature. Okay, so the right answer is C. A is wrong because it has nothing to do with the changing enthalpy. B is wrong because the rates are typically described by collision theory. D is wrong because no, because that's the role for equilibrium quotients. Question 2, the equilibrium constant of reaction is given as 10 to the power 4 or 25 degrees Celsius. Okay, which one? The following statement is correct. So the correct answer is that the forward reaction determined by KQ is therefore unfavorable, and the system consists of mostly reactant because the small value of KQ, right? So D is correct. A is correct, is not true. System is not like necessarily at equilibrium. B is not true. Concentration of the reactants and product are equal, so that's also not true. They don't have to be equal, and especially in this case, not equal. Right. Question C. Forward reaction is favorable, and the system consists of mostly products at equilibrium. That's not true. Okay. If this is true, it will correspond to a larger KQ. Question 3, hydrogen and nitrogen can form ammonia in equilibrium. Okay, so the expression of equilibrium constant, this is pretty trivial. Just recall the equation for Haber process and keep track of the molar ratios. Question 4, certain temperature KQ is 75 for the following reaction, converting ozone to oxygen gas. Okay, so 0.3 moles of ozone and 1.5 moles of oxygen gas was reduced to 5-liter reaction vessel, which for off the table correctly identifies the direction of the equilibrium. So in this question, you first of all calculate the equilibrium quotient. Okay, you calculate the equilibrium quotient and you compare it with the equilibrium constant, and you will see that equilibrium quotient is smaller than KEQ. Right, during the calculation, don't forget to keep track of your volume because they give you the stuff in moles, so you have to divide with volume to get concentrations. Okay, and then you compare. Okay, so D is the right answer. Question 5 to 7, combustion of the carbon monoxide. Okay, yeah, question 5 is pretty trivial. Okay, question 6, consider the following reaction. Okay, so that reaction has like basically this primary reaction with molar ratio times by 2. So that means your like KQ, okay? Everything must also be sort of squared, okay? Because everything's like times by 2. That means like this thing is 4, this thing is 4, this thing is 2. So that means like the original equilibrium constant squared, okay? Question 7, the volume of the system increases. Okay, which of the following is correct regarding to the immediate effect of this change? Volume is increased, it does not increase our K, but it changes the Q. Okay, because volume increase changes the current concentration, and current concentration becomes like deviated away from equilibrium. So your Q changes, right? The concentration changes, Q changes, but equilibrium constant still stays the same. Because the only factor of K is temperature. 8 to 9. Okay, so at 400 Kelvin, the equilibrium constant KEQ for this reaction is this. What can be inferred about this information? Okay, so it's given that at a smaller temperature, K is that. So at a higher temperature, K has reduced. That means at a higher temperature, equilibrium position is toward the left. Okay, that means that if you increase temperature, system actually shifts left. Okay, so the leftward direction must be endothermic. Okay, that means the forward must be exothermic. Okay, by Electrostatic principle. Question 9. At time t, the concentration of the 4 gases are shown in the table below. The following statement is correct at time t. Okay, so the forward reaction rate is now faster than the reverse reaction rate. Okay, so again, use these values, calculate equilibrium quotient, right, and then compare with K. Well, in this case, it will see how equilibrium quotient is actually smaller than the equilibrium constant. So Q has to increase to approach K. Therefore, the reaction must shift forward. Therefore, the forward reaction has a faster rate. Okay. Question 10. Hydrogen gas react with iodine gas to form hydrogen iodide. This reaction at equilibrium concentration of that is follows this, and this. What is the volume? Value of equilibrium constants is pretty much a substitution of values. Okay. Question 11. This is a revision question. Okay. Compare static and dynamic equilibrium. Okay, so I'm gonna skip talking about this part. You guys can take note of my answer. Okay. Yeah, it's pretty much just the comparison. Talk about the rates and talk about the macroscopic and microscopic changes. Okay. Yeah. So and then the part B is photosynthesis being a non-equilibrium system. So for this question, you have to say how photosynthesis is extremely non-spontaneous, and it is made spontaneous based on a bunch of like biological process. So it cannot be like it's not reversible, so that it cannot be forming a dynamic equilibrium. Therefore, it's a non-equilibrium system. It's quite trivial. Make sure you understand it. Question 12. Question 12 gives you a volume of the vessel and the equilibrium moles of all the stuff, right? So part A is pretty easy. Make sure you balance the chemical equation and use the correct error. Right. Part B just asks you to calculate the equilibrium constant, so you can just get the equation from its definition. Right, write this down, and then when you substituting the concentrations, make sure you divide by the volume. Okay, don't just put the moles in. This is concentration divide. So the final answer should be 1.24 times 10 to the power of -3 moles. Okay, actually unit doesn't matter here. Okay, 2 sig fixed. Sorry, 3 sig fixed because these numbers are 3 sig fixed. Question C. While maintaining constant temperature, the pressure inside the vessel is suddenly increased. Using collision theory to explain what would happen. So you should say something like, when pressure has increased, it will cause the rate of collisions to increase between particles. Now, since there are equal amounts of gas particles on the left-hand side and the right-hand side, this actually increases the amount of successful collision the same amount, i.e. this also causes the increasing rate for the same amount. Because the rates are increased by the same amount, there will be no shift in equilibrium. Okay, there will be no shift in equilibrium. There's not going to be any change to the equilibrium constant, because equilibrium constant is only a factor of temperature. Since temperature remains constant, and also since there's no change in position as well, so everything is like it just happens to be faster, but everything is still the same. Question 13 gives you this equilibrium reaction, and it's endothermic forward, tells you the equilibrium constant, and it also tells you a bunch of other stuff, such as the volume of the vessel, and yeah, and then the final equilibrium concentration for hydrogen. Okay, so yeah, a lot of information here. So like it's basically I want you to practice using your ICE table for this question. First of all, we can calculate, right, the equilibrium concentration for hydrogen bromide. Yeah, because it tells you that the equilibrium concentration for hydrogen gas was this much, because the reaction forms hydrogen gas and bromine gas in same molar ratio. That means hydrogen gas and bromine gas should have the same concentrations at the end, meaning that you can use it at equilibrium. You can calculate the equilibrium concentration for your reactor, is HBr here. Rearrange from your equilibrium constant expression, and you should get the concentration for HBr at equilibrium equals to 3.96 times 10 power -3. Okay, make sure to keep track of all the like concentrations divided by the volume as well. Okay, and taking square root and stuff. And then we can construct our ICE table. Let the initial HBr concentration be X. That's what we want to find. Okay, and yeah, and then the others start with 0. And then we know the equilibrium concentration is 9.5, yada, yada, yada. So you know the change, and from that change, and then the molar ratio tells you that HBr must take away 2 times 9.5 times 10 to the power -4 in order to reach this, okay? Right, so then you can calculate what x is just based on this this column right here by setting up this equation and solve for x. Okay. It is quite easy if you get your head around this. Okay. So let me know if you have any question on this question. Question B, after a while, the heat source is turned off, so there's no longer any heat supplied to it. The temperature will reduce, okay? What is the effect of this on the change of equilibrium constant? So remember that temperature will change the equilibrium constant, okay? So say something like during the process, the temperature will reduce, okay? Then by Le Chatelet principle, define it first, okay? Equilibrium will shift to minimize the initial change. In this case, the equilibrium shift to the left, so that to produce more heat, right? Because the reverse direction will be exothermic, okay? And yeah, this results in an increased concentration for the reactants, coming with a reduction in the concentration for the product. And because of that, by KEQ's definition, it's product ratio to reactants. So since like product has decreased, the equilibrium constant will be reduced, okay? Question 14, the following equilibrium, okay, 20-liter vessel, this much grams, so give you initial amount in grams, so make sure to convert that into moles per liter. Okay, so that's what we did initially. So it's asking to calculate the equilibrium constant at this temperature. So yeah, so like the concentration is equal to moles over volume, which is equal to mass over molar mass times volume. Substitute values 100 divided by the molar mass of phosphorus pentachloride, and then times by the 20 liters. Okay, you get this right as the concentration for PCl5. Construct the ICE table, and yeah, basically use the last row to calculate the equilibrium constant. Okay, explain two ways the concentration of chlorine gas at equilibrium can be increased. Okay, so first of all, I answer this question with a definition of what LCP says, because I'm going to use LCP, and then I use two dot points to discuss like the two ways, okay? So the two ways here, first way I chose is temperature change. We can pump more heat into the system so that the system shifts forward to reduce the heat and then therefore produce more chlorine gas, okay? Since I have already defined LCP above, I don't even need to mention it here, okay? And then the next way is to increase the concentration of your reactants, which is the PCl5, and that will cause the equilibrium shift forward, therefore minimizing the increasing concentration of PCl5 as the initial disturbance, and then still causing more chlorine gas to increase its concentration. This question must be careful because you cannot mention like pressure change, yeah? Because if you mention pressure change, right, say if you want to shift equilibrium forward, you must decrease your volume so that you increase your volume, and then you decrease your pressure because of that, and then the system will shift to the right, okay, to increase the pressure. Yeah, but because your initial disturbance has decreased the pressure by increasing volume, that means the initial concentration for chlorine gas is also going to reduce. And then the equilibrium shift trying to minimize that reduction in the chlorine gas concentration, it will not end up with a final increase of chlorine gas concentration. And that's not what we want, okay? We not only want equilibrium to shift forward, but we also want to have chlorine gas to be literally more than before, okay? So you can't say anything about pressure here, so it doesn't achieve the goal with pressure. If you set pressure, I'll mark you up. Question 15. Yeah, so the Haber process involves the synthetic process of ammonia from hydrogen and nitrogen, given us this reaction KEQ is equal to 5 at 298 Kelvin. A chemist pumps 1 mole of this and yada yada yada. Okay, see these are all the initial stuff. Okay, show that the reaction is not initially at equilibrium and predict how the quantity of gas will change so that the reaction reaches equilibrium. Again, we calculate equilibrium quotient for this given this amount, okay, and then compare with K. See how equilibrium quotient end up to be 7.03, which is larger than the KQ, meaning that it's not at equilibrium because it's not equal, and then it will shift to the left in order to convert your Q and approaches to K. Okay, as a result, ammonia decreases and then the reactants will increase in its concentration. Question B, to improve the production of ammonia, the chemist separates and liquefies ammonia that is being formed, justify the chemist's action. So chemist actually converts the gaseous ammonia into liquid. That's what liquefied means, right? So this step actually reduces the concentration of ammonia right here, and then causes the equilibrium to shift forward by Le Chatelier's principle. Make sure to define it. Okay. So in this case, the Haber process actually shift towards to produce more ammonia. This will increase the yield of ammonia. Okay. All right. So basically, this is the technique that industrial chemists are trying to use, okay, in order to extract stuff from a reaction vessel. You can change it into like this liquid state, and then you can pour it out, and then the reaction can also be shifted by that method. It's quite smart. Question 16. It's a concentration graph rather than a molar. It's a number of moles graph, okay, but it's still sort of roughly the same, right? To calculate the equilibrium constant, so we know that equilibrium constant is evaluated when everything has an equal concentration. So that would correspond to the time after like when everything's flat. Okay, so if you just use that value, make sure to convert it into concentration before you substitute the values. Okay, you get 13. 260. Okay, it's quite easy for this question. Question 16b says that to use collision theory, explain the trend shown by the graph. Well, you just have to say how initially everything changes and stuff, okay? So what I said was like at T0, collision rate between carbon monoxide and chlorine molecules is much faster because you only have reactants, okay? Is that reactants? Yeah, because like you only have reactants. You don't have any product. So by collision theory, it's like more successful collision, so the forward rate is larger than the reverse. As a result, you'll slowly form your reactant. Sorry, your product. So consequently, the rate for forward and reverse reaction would also decrease respectively as these change. Okay, as these change continues goes on, it will slowly become reaching a equilibrium state, and then the concentration stops changing. Okay. Okay, so have a read of the sample answer, see if there's anything that you can improve on. 17 says write the overall equation. The overall equation is pretty much just like your net ionic equation. Just add everything up and cancel out the similar reagents. Okay, if you've done so, you will get this equation as your final answer. And then question B, given that the above reaction occurs at the same temperature, find the equilibrium constant for the overall reaction. Okay, so if you have a rid of extension material, we know that coupled equation have a coupled equilibrium constant as well. You could also show it with this with algebra. Okay, so the equilibrium constant for this net reaction is actually the multiplication of the two equilibrium constants together at the same temperature. Or if you done so, you will get this as your answer. Okay. And then question 18. Question 18 has a typo here. So this is actually iron 3 nitrate. Okay. All right. So with that in mind, question A, explain whether significant reaction will occur. No. Because the equilibrium constant for forward reaction is too small. Okay. And then sort of talk about how like at dynamic equilibrium, the ratio is too small to have any significant product. And then part B, determine the value of equilibrium constant. This is just a reverse reaction. So if it's reversed, it's just 1 over the initial equilibrium constant. So yeah, in this case, it will actually be 10 to the power of 10 is a very large number. Now, because of that, the reverse reaction is extremely favored, okay, because the larger KEQ. And that's essentially part C. Okay. Question 19 is this reaction. Okay, this reaction investigates a little bit of the extension material on section 5.3. Okay, so we notice how the general Gibbs free energy change can be related to the temperature independent standard Gibbs free energy change with a contribution to the equilibrium quotient. So you can calculate equilibrium quotient using the value given, and then use the equation I gave you on the booklets, and you can calculate the general Gibbs free energy. It has to be negative. Okay. Be careful of your units, right? Because R is actually in unit of joules, and then delta G was given in a unit of kilojoules, so it's quite different. Part B says to calculate the value of equilibrium constants for this reaction. And if you had a look at some of the extension material, you should also know that at dynamic equilibrium, every macroscopic change goes to 0. So that means delta G, general delta G goes to 0. You can rearrange for your, and then your Q becomes KEQ, right? And you can rearrange for your delta G to get that equation, and then you can rearrange for KQ to finally get the value using your delta G in standard condition. Okay. So yeah. So let me know if you have any questions, and this is it for this week's homework. Okay, enjoy chemistry. I'll see you next time.